want to find interesting in what I'm doing. And I realized that throughout his career, he was interested in threshold effects, light polarization effects, electron correlations, and all of those are involved in strong field physics. And I hoped when I wrote the abstract to show you all these connections. First, though, let me thank my collaborators. These are those from my own group, former graduate student Bogdan Borka, postdocs Gerard Lagmago-Kamta and Dejan Milosevic. And over the past 4 years, we've had a very fruitful collaboration with the group of Nikolai Manikov at Voronezh State University and his two students, Sasha Flegel and Misha Frolov. Misha is now a postdoc in my group. I realized, though, in preparing this talk, that I have too much, and so I'm going to have to cut. And so I will probably end my talk here talking about threshold effects and light polarization effects. If you're charitable to me, you will believe me when I say that I'm choosing to talk about my most recent results. That's how I selected. If you're cynical, you will notice that this work is supported by NSF, this is supported by DOE, and Joe Deemer is here, and Pat isn't.
He can carry the message.
I have to get through some theory. I'm going to give you a 5-minute crash course. What we have done, Nikolai Manikov and my group, is we've taken a reasonable model for an atom, a short-range potential, and we've managed over the last 4 years to develop codes that solve it essentially exactly. And what I'm going to show you are the fruits of this effort. But I want to, since we spent time on the theory, show you the rudiments of it. We have a laser propagating along K, and we assume it's elliptically polarized with major polarization axis epsilon. And the ellipticity can have two signs. It can be either right-handed or left-handed. And you can characterize it, the ellipticity, by the degree of circular polarization or the degree of linear polarization, as you like. We solved the time-dependent Schrödinger equation for a single electron, where this is the atomic potential and this is the coupling with the laser field, described by this A vector, and the electric field, the amplitude of the laser is given in this way. In the quasi-energy, quasi-stationary state formulation, you assume that the wave function has a part that's periodic in time. And it has an energy here that's complex, where the real part gives you the level of the initial electron in its bound state, and the imaginary part gives you the rate, gamma. If you go to infinity, the periodic wave function can be expanded in terms of certain coefficients and some complex momenta. Momenta are complex because the energy is complex, and also this may be negative. It's important to normalize things properly. Since the energies are complex, you don't have a Hermitian system, so you have to create a dual space to normalize these functions, and not everyone does this. Robin Shakeshaft does it properly, and Debbie Watson does it properly. We define the dual space wave functions in this way, and we can check that we're right, because from the quasi-energy we get, we can take the imaginary part and get the total rate, but then we can take the wave function and calculate each of the partial rates for ionization by a certain number of photons and then add them all up. And when we normalize things this way, we get equality of the two results. So it's self-consistent. Similarly, when you calculate harmonic generation, you should use the dual space wave function here and not the wave function itself to normalize the wave function to get a dipole matrix element. And then the amplitude for harmonic generation, a harmonic with energy n times the initial laser photon, with polarization E prime, you obtain by taking the dot product of the polarization vector with this dipole moment. And now the big simplification here, this is exact so far, is to describe the atom by a zero range potential that acts only at the origin. It has a single bound state, and we use scaled units where all energies are measured by the binding energy of this electron, and all laser strengths are measured by the electric field felt by the bound electron. This enables us to scale our results for various experimental situations. And now how do we calculate this wave function? You look at the r equals 0 limit, and you have a function here that's a function of time. You harmonically expand that, and then this function, this is what takes the real work. You have a set of coupled equations here where these matrix elements are highly oscillatory integrals, but we figured out how to integrate them accurately, and they're normalized this way. And then, once you have those coefficients, the amplitudes that you need to completely define the wave function are given essentially analytically, and you put in the numerical values of your f's here. Everything else are known functions. And with that as introduction now, that's the theory. We now look at the results. One of the things Fano liked to do when you had any theoretical model was to explore parameter space, just vary things. Joe Diemer calculated umpteen phase shifts, and Ravi Rao calculated umpteen effective potentials. Here, in strong field physics, what you have is an ionization rate. That is, you absorb n photons, but this rate depends on the laser parameters. It depends on the laser intensity, the laser frequency, the laser polarization. And so you can explore and map the spectral region. And when you do that, this is from the n 8 photon absorption to up to 55 years what we published. We have more now. You see this very beautiful pattern. Unfortunately, PowerPoint doesn't put it in very good focus, but you see here this black line. What's that? This is the so-called plateau. When you absorb a certain number of photons, the intensities drop until you reach a region here where for a large number of photon absorptions, the rates are effectively the same magnitude. This is called a plateau. And I'll show you what the plateau looks later. And then after you get off this plateau, the rates drop. But the interesting thing about this figure is what happens when here's the 8 photon rate is closing, the channel is being closed. You see these structures here. The 10th photon rate is closing here. You see these structures, including a great increase here, a decrease here. What are these things? Well, we immediately interpreted these as explaining a few-year-old problem. That is that in strong field physics, people have looked at the ATI plateau, that is these rates as a function of number of photons, and they found that these, in certain laser intensity regions, these magnitudes would change very rapidly. These are the experimental results that found this, and theories were done immediately. Harm Muller did single active electron calculations that reproduced this sensitivity to laser polarization, and his single active electron results proved that double electron resonance couldn't be part of the explanation because he only assumed a single electron. But he attributed the results as his time-dependent results showed that wave function amplitude was mysteriously adding up coherently at particular laser intensities. Kaufold and Becker then did semi-classical analyses that showed that, sure enough, at certain intensities, large numbers of semi-classical orbits add in phase. And that is the interpretation. But we'd like to think that there's a simpler approximation, and it has to do with a 50-year-old multi-channel physics that whenever you have a channel closing, there can be singularities involved. And the channel closing here, I'll write it down here, because experimentalists can tune this closing. This happens when the number of n photons plus the initial energy of the electron minus the wiggle energy due to the ponderable motive potential equals 0. And notice that you can tune where the 0 occurs by either changing the frequency or the laser amplitude. Now, the well-known multi-channel physics was Wigner-Bose-Wright theory. Wigner looked at short-range potentials and said that the threshold behavior depends on the angular momentum. And in particular, when you have s electrons, you can get singularities at the threshold. Bose showed that other channels that are open are affected by this singularity. And they have similar square root singularities due to S-wave behavior on either side of the threshold. So the cross-section above threshold is of this form, below threshold is of this form, and depending on whether this is plus or minus, you can have 4 characteristic shapes. And this is taken straight out of Landau and Lifshitz. It's all there.
Of course.
So what do we have? Let me show you a bigger, better picture. Here's a blow-up of our latest results that go up to 73. What I'm going to do is look at 3 different intensities here. This is at the closing of the 10th multiphoton channel, and these are intensities on either side of it. And you can see what we're going to take a cut through this, just plot these magnitudes in a line versus the number of photons being absorbed. And what you see is this. At an intensity, an amplitude, I often say intensity, this is the amplitude 0.153, you have this plateau feature and then a drop for the ionization rate as a function of the number of photons absorbed. When you're right at the closing of the 10th channel, this increases by roughly an order of magnitude before decreasing. And then when you go beyond that, it drops again. Now, Bose theory, multi-channel theory, applies for all possible channels, and ATI effects, ionization is not the only possible channel. The electron can recombine and emit a harmonic. And so if you look, this was published in May of this year, if you look at the harmonics on the plateau, and these have been artificially multiplied by a factor of 10 to the minus 2 each on this log scale to separate the curves. Their intensities are all about the same because they lie on a plateau. But you can see at the closing of the 14th channel here, these very sharp structures. You see all possible Bose shapes in these structures. And if you plot the results, you see that here too, there's a look at the closing of the 14th channel. If you're just below the intensity that closes it, you have this curve. If you're right on it, you go up by almost an order of magnitude over a wide range of harmonics. And then you go beyond the closing and it drops down again. So this is a very general feature. And even though we have done these calculations for short-range potential, and the experiments that have seen this have been for neutral atoms, the experiments, not for harmonic generation, but for the ATI results I showed, show very similar results to what we calculate. This is something, why this is so, I don't know, but I will talk about this again. Now, let me talk about the next topic, light polarization effects in strong field physics. What this means is that this rate, which for absorption, for ionization by n photons, depends on the degree of, on the sign of the laser helicity. whether it's right-handed or left-handed. There's an elliptic dichroism effect, and this is a very interesting effect. It means that if you have right-handed elliptic polarization and left-handed, the difference of these two rates is not zero. Now, elliptic dichroism is not a generalization of circular dichroism. In fact, it's zero if you have perfectly circularly polarized light. It has a different physical origin from circular polarization. Of course, it vanishes for linear polarization. What's essential for elliptic dichroism is that one have rescattering from the initial potential. You must include that in your calculation, and this was recognized early on. But the Keldysh approximation, which ignores any rescattering, it says the potential is there just to hold the electron like a golf tee to hold a golf ball, and then from then on the electron is free. That never predicts elliptic dichroism. But if you include, even to first order, as did Becker, rescattering, at least one rescattering, you get a non-zero elliptic dichroism. And at this point, let me just give a little bit of the history. Above threshold ionization rates with elliptically polarized light, a group, Phil Buxbaum's group, was the first to show that the symmetries were different with elliptically polarized light. You didn't have a symmetry that was expected. 10 years later, Paulus did a very careful study with, and I will close this talk with a comparison with his experimental results. The theory, very quickly, a number of people, including Peter, explained that in order to see this asymmetry in the angular distribution, you must have rescattering. So this is understood fairly quickly. And more recently, careful systematic studies of the ellipticity dependence have been done, but the focus has been on having a particular frequency, a particular laser intensity, and looking at how it varies with polarization. What I want to do is look at the variation with intensity and frequency and see the physical origin of this effect and where you can find it. First of all, I want to show how much do I have? Good. What I'm showing here, and it may be difficult to see in the back, are three different theoretical calculations of these ionization rates as a function of the number of photons. The simplest approximation is the Keldysh approximation with no rescattering. The electron is free once it's ionized, and you can see here that that just continually decreases. You don't get a plateau. This is something that's well known. But you must have rescattering to get this plateau feature, and you can get it with just treating a single rescattering of the electron with the potential. In our calculations, we have infinite number of rescatterings, and that's the solid line. So you can see as far as the total rates are concerned, you just lower the results. But now the more interesting physics comes from the angular distributions. These curves are angular distributions at different points in this figure. So you can see this n equals 15 here is well in the region where the simplest approximations work. All calculations give the same angular distribution. They're all symmetric, about 0 degrees of emission relative to the major axis of polarization. As you go toward the beginning of the plateau, this is where the interesting stuff starts to happen. In particular, look at n equals 27 here. This is just as the plateau is forming. You can see here the Keldysh results give a symmetric curve. The exact results, our exact results, the solid curve, give 3 peaks, of which this is the highest, and then it decreases. If you just include one rescattering, you get qualitatively different behavior. The second peak here is the highest, and then the third peak is lower. So the most striking differences occur right at the beginning of this plateau, where it's forming. as you get well on the plateau, as these two figures are, you can see that including one rescattering and multiple rescattering gives you qualitatively the same features, but the exact results are a factor of 2 or so lower. So now, let's look at the ellipticity dependence. What we have here are 3 curves for different ellipticities. Eta equals 1 would be circularly polarized. Eta equals 0 would be linearly polarized. You don't get any elliptic dichroism for those two cases, so we didn't plot them here. But you can see here, I'm just going to look at the 28 photon rate as a function of ellipticity. And what I want you to see is that right where at this ellipticity, 0.4, where the plateau is just beginning to form, that's where the major elliptic dichroism occurs. Once you get up here, it's less, and down here, there's very little. So let's look at that n equals 28 rate. You see here, this is 0.2, 0.4. Here, as I predicted, this is where the solid line gives you right-handed elliptic polarization. Dotted line gives you left-handed polarization. You see a big difference between the right-handed and the left-handed results. That difference vanishes when you get close to circular polarization, and it's smaller when you get well on the plateau. So right at where the plateau is beginning to form, this is where the biggest effects form. Now let's look at the intensity dependence. Here are a bunch of rates plotted now for different laser intensities, not ellipticities. Again, as a number of photons. If you look at the rate for 44 photon absorption, as you change the laser intensity, one could just predict that this point here, which is after the plateau, is not going to have any elliptic dichroism. These results here, which are toward the beginnings of these plateaus, should have strong elliptic dichroism. And this one, before the plateau forms, will have hardly any. Let's look and see. If we go to 44, that's this row here, you can see that the 3 curves that I circled are these 3, and there the difference between the right-handed and left-handed polarization is very large. As you get on the plateau, the differences become smaller, and similarly, when you get below the plateau, they also are small. So it looks like exactly where the plateau is beginning to form, this is where the interesting physics is happening, that the system is very sensitive to the handedness of the incident light. And I promised to show a comparison with experiment. Here we have a recent experiment of Paulus and his group in Garking, where they have, in this figure here, plotted the angular distribution for absorbing 15, 17, up to 25 photons. 15 to 21 are in the Keldysh regime. And so we expect roughly similar symmetric peaks. N equals 23 and 25 are the critical region where the plateau is just beginning to form, and so that's where we expect the peaks to be most asymmetric. These are our calculations. And you can see here that there's a discrepancy for 15 photons. This is a very broad structured peak. We predict something symmetric with a deep minimum here. That doesn't agree there. But beginning with 17 and on up to 25, there's remarkable qualitative agreement. For 17 and 19, the experiment predicts a lower left-handed peak and a higher right-handed one, and that's what we find. When you get to 21, this reverses experimentally. You get the left hand higher than the right-hand one, and that's exactly what we find. For 23, we predict the left hand is twice as big as the right hand, and that's what the experiment finds. And then here, for 25, we predict a structured, much lower peak, and the experiment sees a rather broad, low peak. And we are extremely surprised that our model for a short-range potential is able to mimic the experiment done for argon, a neutral atom that sees where the electrons see a Coulomb field afterwards. But this is one of the mysteries of strong field physics, that atomic models, you need them, but on the other hand, their details don't seem to be all that critical. Let me just finish with one more slide before I give my conclusions. And this is, so far, all the results I've shown you have been in this region where these elliptic dichroism effects are at fairly low intensity, and rescattering is the major reason why you have the effect. If we push our calculations to much higher intensity and look at the total elliptic dichroism effect, this is summed over all absorbed photons, where we subtract the difference of right and left-handedness, our results show this declining behavior. And we wanted to understand, why is this declining? Well, we interpret this as a measure of the amount of dissipation in the system. The reason is that the dashed line is calculated where we assume that the quasi-energy, the energy we have, is real. We take only the real part. We throw out the complex part. The complex part is essentially the rate, the total rate. And so when we throw out the total rate, our curve becomes essentially flat. So at high intensities, it seems that the dissipation in the system is driving the qualitative behavior. Whereas at low intensities, it's the rescattering that is most important. So I think I'm about done. 3 minutes? Well, I was going to show you about electron correlation effects, but I guess I will postpone that in the interest of time. And just conclude that these threshold-related anomalies in both above-threshold ionization and high-order harmonic generation demonstrate that even in strong field physics, well-known interchannel interactions are important. And this was not always obvious. You can think of strong lasers as essentially controlling free electrons. And as the other talks show, in double ionization, people are searching for signatures of where correlation is important. Here, we're showing that interchannel effects are also important. Secondly, these elliptic dichroism effects really provide information on particular interactions of lasers with atoms that are sensitive to laser helicity. So with that, I regret that I wasn't able to cover the last topic, but I'll conclude.